Hello everyone. Welcome to this webinar on Kalman filter for state of charge estimation. I am Abhinav Arvind and I work with Decibels Lab as a VMS algorithm development engineer since 2021. And I have been primarily involved in creating model-based designs of work related to like cell modeling and BMS algorithm modeling, and also involved in testing and validation of the algorithm. So apart from that, at the facility we have here in Bangalore, I'm also involved in testing of many cells, that is lithium-ion cells, for the various applications, like for EV and for like two-wheeler EVs and things like that. Right. So in today's session, we will be covering one of the important algorithms that is used widely for something like state of charge or like even other states estimation. So here we'll be discussing on the Kalman filter. Okay. So the idea of this webinar is to represent or to deliver just a very basic overview or like a surface view on how Kalman filters work, and what are the main involved processes in the Kalman filter, and a quick overview on what the model looks like. So how exactly the model for this Kalman filter is developed, and eventually what are the results that you can expect, and some few key parameters of the model that will help you decide how to choose the right approach for this particular model. Okay, so with that, we will start today's webinar. So here is today's contents. So rather, here are the today's delivered contents for what are all the topics involved today. So first we will start with like what is the necessity of estimating state of charge. So why we go for estimating state of charge, or what is the requirement, right? So it is very important, especially when it comes to EVs, electric vehicles, especially when you're going for like long distance travels. It is important always to know what is your current available state of charge, or what is the present SOC of the battery, so that we know like many parameters like range, distance traveled, etc. Then we have the different SOC estimation methods. So there are three estimation methods. So this will be like broadly discussed when we get to that particular topic. So here, just quickly, we will see. So first one is called as lookup. Okay, so also it is called as voltage lookup based method. The second one is called uh, current integration. And the third one is a fusion method, or you can say it is a combination of the first two, and which basically retains the properties of the first two methods and kind of like balances out all of the advantages and disadvantages. Okay, so this will be discussed in little bit more detail when we get to this part of the session. The next, we will then go into Kalman filter, the structure of the Kalman filter, like what exactly does the structure contain. So pictorially, we will be seeing, or figuratively, we will be seeing how the algorithm looks like. And then stage by stage, we will see each and every step that has been involved in designing the algorithm, the Kalman filter algorithm. So that structure that we will see, it is common to all the different varieties of Kalman filters, except for like the type of modifications that is relevant to that particular type of Kalman filter. Okay. So here I'm going to explain the skeletal work, or basically like the structure of the algorithm. So after this, we will see a quick overview of the Kalman filter model. So that model basically what is the inputs, what are the outputs, what are the like some of the interior components, what are all used in there, that particular type of model, that we will see. And then after that, we will have a quick overview on what the results will look like. So once you simulate the model, we will see like how it looks like for constant current and pulse power characterization, or basically it's also called as pulse profile. And we will also have a quick overview on what could be the possible results that can be used as a validation point. Okay. So these are your overview of the results. And then we come to the final topic, that is on further improvements to Kalman filter. So like there are many different varieties of Kalman filter, or you can say many sort of categories of Kalman filter. And ones that have been like on recent focus is basically what is called as adaptive Kalman filter and uncentered Kalman filter. So what are the properties of these two? We will have a look at that as the final section. Okay. So with that, we will start with the first topic. So here the question arises that why is it necessary to estimate the state of charge, or what is the requirement to estimate the state of charge? So like we know state of charge is just easily, it is representable as estimated or available capacity, or you can also call this as present capacity. Present capacity divided by rated capacity, or you can also call this as nominal capacity, right? So this nominal capacity is given by the battery manufacturer, while present capacity is purely dependent on like how we estimate the value. Okay. So like later we will see what are the estimation methods, right? So the purpose of estimating your state of charge, or like you can say measurement of SOC, state of charge, is because the following vehicle parameters is very important, like total vehicle range. So like total vehicle range in terms of available range, you can say available range. So this will give you an idea of how much range is left, right? So also another very important parameter is what is the current internal resistance, because this will help understand what is the current condition, or you can say the health of the battery. Okay, so internal resistance is very, very reliant on SOC, because the batteries don't have constant resistance throughout the state of charge. So it will have a varying like graph with respect to SOC. So if you take how the resistance looks like, it looks something like this. So if you start at 0% and move to like 100%, your resistance, that is your IR, internal resistance, varies quite a lot with respect to SOC. So if you determine the internal resistance, it gives a good idea on what is the current condition, or you can see even the health of the battery, the present health of the battery. So another important aspect is to also determine the remaining battery capacity. So this will actually help determine like, okay, at what point the charging can start, what point the charging can stop. And likewise, with respect to charging, with respect to charging stopping and starting. So here you can also control your uh, overcharging or over discharging. So these are all like your most important points that you can see, or you can like collectively understand. So when we say why SOC estimation is important, okay. So not only this, there are many more like uh, parameters which can be estimated, like temperature and other things like energy, state of power, and all those things, which is like a sort of a derivative taken from the state of charge. Okay. So of course we also have the most important aspect, which is the state of health. So if you don't know the state of health, if you don't know the state of charge, then you do not know the correct condition of the battery. If you don't know the condition, then we don't know to what extent the battery has degraded. So therefore, we don't know till what extent the battery can be used. So SOC can once again be used as somewhat of a derivative. Uh, it cannot be used directly, but it can be used as like one of the ways in which you can estimate the condition. Okay. So this is like the most important few points that you can say, which is for like the requirement for SOC estimation. Okay. And here you can see what are the different methods, or what are the different SOC like estimation methods that is widely used, that are have been well established in today's algorithm development field, or you can say the research field. So like the first and foremost method is called as OCV to SOC lookup table. Okay, so OCV stands for open circuit voltage and SOC is state of charge. So if you take a simple one-dimensional lookup table, which like I'm writing as LUT. LUT is nothing but lookup table. So if you use this, it's one of the simplest ways in which you can estimate the state of charge based on what is the measured voltage at a particular point in time. So for example, let's say that uh, the vehicle has discharged the battery as from a certain point like this, and once it has stopped, so here after some rest period, then you can say that the vehicle has reached what you can say as OCV or open circuit voltage condition, or in other words, it is also called as steady state voltage. Steady state voltage condition. So there you can use like a lookup table, or you can say a set of reference values, uh, which you can like have use which you can input using a certain map or one-dimensional map. Okay, so it will look something like this. So if this is your measured value, that is your measured open circuit voltage, or you can also say measured voltage. And if this is your SOC, state of charge, then like for every like value of voltage, like for example, some recorded values are there. So for example, like 4.2, then like 3.9, 3.7, 3.5, so on, till like say for example at some end voltage, so like 2.9 or 2.8. Just I'm showing some example values here. Then you can then some fixed values of state of charge is provided here. So for example 4.2 is generally considered as 100%, and then like this will go on like 90%, 80, 70, so on, and at the last this will be like around 0%. Okay, so the manufacturers will or OEMs will usually go for adjusting these voltage values as per their requirement. It is not necessary that they'll go all the way till 2.8 volts. They can consider even slightly higher value as 0%, depending upon the vehicle design. So this is one way of like estimating the state of charge from the open circuit voltage method, and this method is called as lookup table method, LUT. So this is one of the simplest and one of the most direct ways of estimating the uh, state of charge based on what voltage reading is provided. Okay, so later we will see like what are the drawbacks of this. So in the next slide, we will have a comparison to all these methods, and we will see like what is the advantages or disadvantages, right? So apart from lookup table, we have something a little bit more advanced, or you can say a bit more like you can say a bit more accurate. It is called Coulomb counting. Okay, so Coulomb counting or current integration, basically it is nothing but the continuous integration of current with respect to time, and if you take that as a ratio with respect to rated capacity, then you can obtain the state of charge. So this is like very simple as well. So this is a direct method once again, which requires no such thing like table or no such thing as reference values. It just requires a rated capacity. So like again, you need to input the rated capacity here from the manufacturer values, and you also have to have an initial estimate of state of charge. So basically, from what point the state of charge calculation is starting. Okay. So once again, we will see what are the problems with respect to this in the next slide. Okay. So to make this a little bit more accurate, there is another method. It's called modified Coulomb counting. So which shows like little bit of marginal improvements. So there is like a major problem with Coulomb counting, which is called as like accumulation of error. So that drawback we will see again in the next slide. So apart from the two types of Coulomb counting, we also come to the last part, which is like the most advanced. It is called filtering based, or you can say recursive least squares based method, in which Kalman filter is one of the most like widely used methods in this type. Okay, so it is a fusion approach. It is also called as fusion approach, which retains the properties of both lookup table based and also the Coulomb counting based or current integration based. Okay, so it's kind of like an approach that uses both the logics of both these methods. Okay, so now these are like the most well established, or you can say the most well known methods for state of charge. But what are the drawbacks, or you can say what are the properties of each of these methods? Not all methods are perfect, right? So what could be, or what are the well known properties of each of these methods? So first we will start with comparing the voltage lookup based, then we will look for Coulomb counting, then we'll go for Kalman filter, right? So then first and foremost, the voltage based method, we have seen it is very simple. It does not require any high level computation. It is very simple. It just is a simple map, a one dimensional map that compares the recorded, or you can say the measured voltage value to the pre-established values of state of charge, right? So the assumption here is that you must model the voltage to SOC values very correctly. So like the reason for that is because it is extremely sensitive to temperature and also requires an extremely accurate measurement of voltage. So then again, this is like very heavily dependent on the hardware, the capability of measuring the voltage to a very good accurate value. So for example, like if you have some accuracy of say plus minus 0.05 volts, to a certain extent, this can be like agreed that this is fairly accurate, right? Because this is in the hundredth decimal. But if you're having like variation, say for example 0.08, sorry 0.8 volts or something like 0.5 volts, so this value is actually considered like very high, and this is inaccurate. So if this recorded value or measured value of voltage itself is inaccurate, then your measured value of state of charge also will be inaccurate. So therefore, your lookup table must be must account for change in temperature, and also you must have a sensor with good amount of hardware that can measure good accuracy of voltage. So the drawback is how well your OCV curve is represented in the table. Okay, so not always this kind of method is preferred. So especially when we're going for very high level of computation, or when you're going for like very accurate estimation and representation of state of charge, then for that purpose we cannot go for voltage based lookup, because like this won't yield, or this will not give correct results, right? So that is where slightly more accurate value is Coulomb counting. So Coulomb counting, here like you can have like some degree of sensitivity to temperature, right? Since this does not rely directly upon measurement of voltage, rather it depends upon the measurement and integration of current. Okay, so here the lookup table is not used, so there is no lookup table as such here, but instead of this there is uh, like integration of current. So first measurement of current, then integration of current. But again here there is like some drawbacks, that initially your estimate of cell capacity must be very accurate. Okay, so if you have the incorrect like estimate of capacity, then even your estimate of SOC will be incorrect. So then it must be really purely dependent upon how well the preliminary cell testing part has been done. So if the values from the cell testing is correct, then here too the estimate of SOC will be correct, right? So in the previous slide, we had seen that there is a major drawback, that which I talked about, what is called as error accumulation. So that is because of the integration, right? So since the Coulomb counting involves the continuous integration of current with respect to time, there is always some error that is accumulated because of the constants that are generated after integration. Okay, so that's basically that is what is called as integration error. So over time, this leads to what is called as SOC drift, or you can say like uh, change in the estimated SOC value. For example, let's say that for fresh computations, the state of charge is going correctly, say from for example 100% to around 30%. Okay, but after some time, after like some few computations, it will be like some errors will start to accumulate, and you will see that the SOC will start to drift farther and farther outwards. Okay, so this is called as error accumulation. Right, so this is actually one of the most fundamental major problems, or you can say one of the fundamental characteristic problems that you will encounter when dealing with Coulomb counting method. So this is like a major drawback. Even like you consider the first point, it is not a major problem, but the second one, it is like one of the major issues. So because of this, the state of charge estimates will become more and more inaccurate as in when the computations go on like proceeding. Okay, so this is like one issue. Apart from this, we also have an issue that it requires a very accurate estimate of the initial state of charge. So this again depends upon like how well the previous state of charge was estimated. Okay, so if you don't have an accurate estimate of initial SOC, then your computation of state of charge won't be accurate. Okay, so apart from this, we also have Kalman filter. So here, as I said, it is a combination of the previous two methods. So that is of lookup table based and Coulomb counting based. So here the thing is that in the previous two cases, like nonlinearity behavior was not correctly considered, or you can say it was not considered to a good extent. But here in Kalman filters, especially in things like EKF, that is extended Kalman filter, and things like UKF, that is unscented Kalman filter, these two methods they can like very well represent the nonlinearity of SOC OCV behavior and even other parameters as well. Okay, so here the limitations are that the system states and certain state equations and state parameters must be very, very well known. Like it is very well, like it is very sensitive to these estimates, or you can say it is very sensitive to these parameters. So if those are not well known, then even your Kalman filter will not be very effective. So that is one limitation. Second thing is that model is very sensitive to process noise and measurement noise. Okay, so these are two types of variations of coming in from the sensor and also from the plant. That is to say, from the system. So these two like values have to be considered. So later we will explore like what exactly is the meaning of process noise and measurement noise, what is the significance of this, and like what is the way in which we can have a estimate of how these two values are like taken into consideration. Okay, so just for your simplicity, the model is very sensitive to process noise and measurement noise. So like these are two types of you can say errors, or you can say two types of disturbances in the measured signal which have to be considered, right? So now we have taken a look at all the properties of the estimation methods. So now we'll go into algorithm overview. So here, this is the state of charge estimation for using Kalman filter, like how exactly the algorithm is established for state of charge estimation. So everything for Kalman filters starts over here, where what is called as initialization step. Okay, so all these filters, it does not matter if it's Kalman filter or recursive least squares or anything, any other type of filter. So what is the first step? The first step is initialize, where all the input values, like for example, initial state values, initial process values, initial noise values, initial measurement values. The basically it is also called as the starting point. So here you can see starting values. They have to be provided here as an input, And from there onwards, the model will start to evaluate the algorithm. So first we start with initialization step, then we go into what is called as state prediction step. Okay, so one by one we will see like what are like the functions involved, what are the equations, and what is the significance of each step, right? Then we'll go into what is called as state update. Then we go into estimating the current system state. Okay, so the state that is the state update is once again dependent upon other things like Kalman gain, observation metrics, and things like these. Okay, so basically all you have to keep in mind is that this state predict and the current system state, that is you can say the updated state will be continuously in loop. Okay, so from here, so again back to this. So this will be in a continuous loop. That is why it is called as a iterative method. Iterative method, or you can also say loop method. So because these two steps will keep continuously running in a loop. Okay. So we will see now step by step how each one is executed, or you can say evaluated, and then we'll come to see like how the model is generated. Okay, the Kalman filter model. So here we will start with the first step, that is initialization. Okay, so let's just quickly, here we see the terminology for the Kalman filter. What are all the terms that we use to depict the complete flow or the complete process of the Kalman filter? So we will like there are a lot of terms, but here you can just see a simplified version of it. So like when we talk about states, so that is represented in the matrix format, or also called as state space format, and they have like certain abbreviations or terminologies, and that is given as A and B. So universally they are referred to as A and B. So each one like corresponds to a type of matrix. They're called as state matrix. Then we go for another terminology which is representing the error or residual. So later we will see how exactly the residual or error is represented. Then we'll see observation matrix. Then we use Kalman gain. Kalman gain is like one of the most important parts of the Kalman filter. Then we have state uncertainty. So uncertainty is some sort of error or deviation from the estimated value. So all like filters or all statistical approaches will have some degree of uncertainty, and that here is represented by P. Then we have process noise and measurement noise. So as I said earlier, these are two types of noises, or you can say unwanted interference in the measured signal and the system. So they also have been considered. So apart from that, you have system input, you have system states, then we have predicted states, updated states, and system uncertainty update. So these are all like the important terminologies. How each of these Kalman filters, it does not matter which Kalman filter, they all utilize the same type of terminology here. Okay, so now we will see like what are system states. So just a quick overview of this. So basically, whenever you consider any system state, it is basically some parameter, or you can say some variable of that particular system that describes the current state or the current condition of that particular system at a given time. Okay, so like for example, in a car at a particular time, you can say that one of the system states or one of the variables is its velocity, or you can say its speed, you can say its distance, you can say its acceleration. These are what are called as system states. Anything which represents the system's condition or the system's behavior at a particular time, that is called as a system state. So for a particular electrochemical cell, so if you take, say, for example, a lithium ion cell, then the state variables are represented as this: state of charge and voltage across the RC branch. Okay, so these are the two like state variables that have been derived. So the derivation of these two variables actually we will not be considering in this particular webinar, because that's a different topic altogether that goes more into like study of individual system behavior and as such. So we won't have enough time, nor we have enough scope to cover it in this particular webinar. So just for the simplicity here, I have mentioned as state of charge and voltage across RC branches. So here again, it depends upon what type of RC branch you are choosing, whether it is 1 RC or 2 RC or whatever. As for example, you are choosing NRC. So like 3 RC, 4 RC, 5 RC. It is dependent upon that. Okay. And correspondingly, even the function here will go on changing. Okay. So here you can see on the right hand side, what is the like variable, what is it a function of? So f of k means usually it is a function of time. Function of time. Okay. So like here you can say that these values are discretized. So you can say that this is a discrete value, discrete function of time. Okay. So basically what happens here is that all the functions that are like represented in time format is converted to discrete format. Okay. So especially when you're dealing with nonlinear systems, we have to go into discrete format rather than going into like continuous time format. Okay. So state of charge and voltage across RC branches, again, even this is in discrete format. So these are the two state variables, and as I said, they can be like further classified into multiple types of voltage across RC branches depending upon what model is being considered. Okay. So these are basically the type of system variables that you can understand for the uh, like when you're going for like system modeling for like state space approach, especially when you're going for discrete approach, right? So now here we come to the steps. So initialization. So as I said earlier, here the execution of the Kalman filter begins, right? So here what we do is we mention the initial values. For example, the process uncertainty, the noise values, the initial state values, the capacity, the current, all these are used as inputs and they're given a certain initial value. Because like the Kalman filter, once again, requires certain amount of initialization and only then it can begin the execution. Okay. After this, we come to state prediction. So what is state prediction? So as we saw in the earlier slide, state is nothing but the possible behavior or the possible condition that the particular system can represent, right? So state prediction is a particular step which requires the possible prediction of the system in the next possible instant of time. Okay. So if we start the initialization and let's say k is equal to 0, then this step predicts what is the possible situation or the possible system state at k is equal to k plus 1, or here you can consider k is equal to 1. Okay. So this is the second step. The third step is what is called as observation matrix. So this is most commonly used in like nonlinear Kalman filters, especially in EKF. Okay. So where a certain degree of nonlinear parameters are linearized to a small extent, so that like the system like reduces the complexity, reduces the system complexity from high order nonlinearity to a certain degree of linearity. Okay. So like again, this will require a separate set of explanation how the observation matrix is derived and how the observation matrix is constructed, because it's a totally like slightly different field of study as of now. So we will not go too far in depth. Just you have to keep in mind that this considers some amount of linearized parameters. Okay. So one example which we can see is that SOC, that is state of charge, is a like it is once again like a function of OCV, or you can say OCV is a function of SOC. So if you take the derivative of this with respect to time, the partial derivative, then you get a part of this linearized parameter. So you're basically linearizing a certain parameter about one of the time steps. So that is one way of considering it. Another way is another way is like taking the partial derivative with respect to SOC itself. So d by d SOC of open circuit voltage. So again, OCV is a function of SOC. Okay. So here these are the ways in which you can consider like some amount of linearized parameters. Okay. So that's basically what your observation matrix does. So next here we have the last three steps, that is error or residual. So whenever we are going to measure error, there are two very fundamental parameters which are considered. One is called as measured value and one is called as predicted value. So in the last slide, we saw something called as predicted state. So something we saw that is called as predicted state. Right? So predicted state is one, and another one is called as measured value, which is coming in from the sensor. So for example, you can say predicted voltage, just as an example, predicted cell voltage versus measured cell voltage. Okay. So measured cell voltage and predicted cell voltage. So error is nothing but the difference in these values. So if you take, say, for example, measured value, measured voltage minus predicted cell voltage, then you get what is called as error or residual. There is another name for this. It is called as innovation. So they all carry the same meaning. It is nothing but the difference in measured value and predicted value. Okay. So this step is very particularly important, especially when you're going for computing the actual value of the system state. That will come to in the next step. Okay. So once we are done with error, so here you can see error is a function of like observed value versus predicted value. Okay. So predicted value comes from the predicted state and observed value comes from the measurement sensor. So there will be like, for example, a voltage sensor. So that will tell you like what is the approximate voltage of the particular cell at this given time. Okay. So next we come to Kalman gain. So the most important thing to note here is that Kalman filter is a statistical approach. So it requires you to provide a certain weighting factor. Okay. And that weighting factor is nothing but Kalman gain. And it has a value between 0 and 1. Okay. So the concept here is very simple. It is basically a set of preference that you're providing, whether you want to provide more weightage or lesser weightage to the error that is estimated here. Okay. So like if you want to say, if you want like to provide more weightage to the say for example the measured value, then in that case you can have a higher Kalman gain. Otherwise you can go for lower Kalman gain, in which the weightage is provided to predicted value. So that way you can like that is how the Kalman gain works. Okay. So it is just a weighting factor. And once we have defined all these parameters, starting from initialization till Kalman gain, then we come to the final stage, that is to say the final step called state update. So here in state update, the predicted state is corrected, or you can say it is updated. So whatever error has been estimated, that error will be like updated using what is called as Kalman gain. Then it will be updated here in this particular step, in the last step, that is the state update. Okay, this is the final step in Kalman filter evaluation. So all Kalman filters, irrespective of what type it is, will contain all these steps. Okay. So this is the complete flow of Kalman filter, especially when you are looking at things like steps beyond regular Kalman filters like EKF or adaptive Kalman filters. All of them consist of these steps, right? So now we will have a quick view of what is called as process noise and measurement noise. So we had come across this in like the first, the third slide, or like the fourth slide, where we had talked like, okay, process noise and measurement noise. So here you can see what are the exact definition of this, what is meant by process noise and what is meant by measurement noise. Okay. So to be quite honest here also, the definition of process noise and measurement noise is not exactly fixed, or it's not, there is no exact way to define it, because like it purely depends upon what type of situation you're dealing with. But most widely or most generally, it is considered as deviation in the system behavior or system estimate. That is process noise. Okay. So how much noise or how much unwanted interference is being generated in the system. For example, like let's say that we are considering a simple a car, in which like we are trying to process the velocity, right? So how much deviation is there in trying to estimate the velocity, that is given as process noise. And measurement noise is how much noise is coming in from the sensors. Okay, so that is purely dependent upon the sensor quality. Okay, so that is the difference between process noise and measurement noise. So like there are two completely different types of uh, estimation of the process noise and measurement noise. It is actually very like advanced for this scope. It is not discussed here, but you can see here what are the possible sources of each type of noise. Okay, so it is little bit more complex to describe process noise because you have to go pretty in depth into understanding how the system itself behaves, right? So like things like unmodeled system dynamics, or something like missing equations, or like missing parameters, some approximations such as like simplifications, or you can say linearization. So any of this, if this exists in the system, then again it can lead to like some sort of process noise, or even uncertainties in estimated parameters. This can all lead to what is called as process noise. Okay, so these are like possible sources. Then on measurement noise, it is purely dependent on the hardware. Something like your sensor inaccuracy. There could be external sources such as EMF signals, some sort of like radio waves, or something like some electro magnetic interferences that can be like something that can be like as an external source, or it can have signal interference because of electrical interference, some wiring issues or damaged components. Even this can cause measurement noise. Okay, so system noise is pure, process noise is purely has to deal with the system. Measurement noise purely has to deal with the sensors. Okay, so this is the difference between the two types of noises, and both these type of noises have to be considered while designing a filter like the Kalman filter. Okay, so here you can see what is the overview of the Kalman filter. So this is actually the model that has been developed here at Decibels Lab. So how what are all the different like inputs to the model, what are all the outputs to the model, here we have considered. Okay, so starting with the same type of initialization values that have been discussed before. So initial system state, like for example, you are providing an initial value for SOC. Okay, so for example, let's assume that the SOC is being initialized as 70%. Okay, and the voltage across the RC branch is given as 0. Okay, this is just an example. So this is one of the initial system states that you can provide. Then you have to provide process noise and measurement noise values. Okay, so once again they're provided in a matrix form. Okay, that is why they're called as covariance matrices. So they'll usually be provided as two-dimensional or three-dimensional matrices, which is basically a diagonal matrix. Okay, so some value, say for example, eta 1, eta 2, and eta 3. So these are like the values that are being like considered. This is the format in which it will be provided, and eta 1, eta 2, eta 3 are values of q. Q is but nothing but your process noise. So basically it is q1, q2, comma q3. Okay, so again this all is derived purely from like electronics point of view, from where we go for something like signal analysis, and like pulse width modulation, and more advanced mathematics which will require like derivation of these values. Okay, so that is another initial value that you have to provide along with the measurement noise. So here measurement noise is usually just considered as a singular value. So something like as an example, 1.5 into 10 raised to minus 3. So it is initialized like this, and later on if updating this value is required, then the Kalman filter inside can be adjusted to take care of this. Another input is your current. So for cells or for batteries, always the input is current, and output will be your updated state. Okay, so cell terminal voltage, which is measured, this is the measured value. Okay, so this is the measured value that is once again taken as an input. Then again, as I said, voltage across the RC branch. So this again will be taken as an initialized value, or you can say this is initialized input value, and time constant. Okay, so time constant is a product of resistance and capacitance. So again, these values will come in from like cell testing and characterization and things like that. Okay. So these are all your inputs to the model. Their model outputs will be your updated state and updated uncertainty. Okay. So these both are your outputs. So as very broadly, it is being shown here, like the complete in-depth portion of the model. Right now, it may not be like completely possible to show it here, but these are your model inputs and model outputs. Okay. So this model has, once again, it has been built in the same exact form with the same exact set of equations and functions that has been discussed earlier, right? So once we create the model, once we provide all the initialization values, and once we provide all of the like structure of the algorithm, we get the simulation outputs. Okay. So here you can see what the simulation outputs look like. Your SOC comparison between Coulomb counting and EKF. You can see here how closely they match, based on what values we provide and what is the error between the values. Okay. So error will always be there. You cannot get a perfectly you can say you cannot get a perfect system with a perfect response. It is not always possible, but there will be like some small amount of error, and that is once again dependent upon, as I said, process noise and measurement noise. Okay. So this is how your outputs will mostly look like. So even for a drive cycle pattern, if you take like some sort of dynamic current profile, it will provide you like a very similar traceability, just like how you are able to see over here. Okay. So now we come to like one of the most important topics of a Kalman filter. So something which Coulomb counting or SOC, OCV lookup table methods will not be able to adjust to this, and it is called as model convergence. So model convergence is basically like how accurately the model is tracing the desired value. Okay. So like idealistically, if you observe, for example, let's say that this is your measured SOC, or you can say this is your measured value, and the Kalman filter is I will use a different color. Yeah, so Kalman filter is like provided at a slightly different starting point. Let's say that the convergence happens like this. So this is more idealistic. So this is basically the kind of model convergence, or you can say the parameter convergence that you would prefer in any model. Okay. But this is, as I said, it is idealistic and it is heavily dependent upon Q and R. That is your process and measurement noise. So the behavior of Kalman filter or any other filter for that fact is very dependent upon how correctly the values of Q and R is chosen. So the thing is that if you choose extremely small values, or basically you can see if you underestimate the values, then it will give you results something like this. Okay, where you can see a very large initial error, and it takes almost 3000 seconds to almost 4000 seconds to converge, right? So basically this kind of error will basically lead to what is called as overshoot. Overshoot. So that means it's estimating an SOC or some sort of parameter much higher than what is actually what is the actual value recorded. Okay. So that way it will give you false indication, and it will give you like false results that that SOC is much higher than what it is actually, what is actually the real SOC. So on the other hand, if you go for like extremely high values of Q and R, or if you go for like overestimate, right? Then you get results something like that, where you see on the bottom, where basically there is absolutely no convergence. Okay, there is very, very large deviation. Either the convergence is very slow, or it is not converging at all, no convergence. So that is why one extremely important aspect is to choose the very like accurate values of Q and R. Okay, that is your process and measurement noise values, which usually is actually taken by trial and error method. One of the like only sort of possible ways which you can estimate Q and R is by going through trial and error, where you would fix a certain value of Q, fix a value of Q, and continuously change R till such time the desired variation, or like the desired error is achieved. Okay, so where you'll see that the error is like representing something more realistic. Okay, so till such time the value of Q can be fixed and R will go on changing. Like as an example, you can set Q is equal to 1.8 into 10 raised to minus 15, and R can continuously change within a certain value, within a certain range. Say for example, 0.5 into 10 raised to minus 3 to around uh, 7.8. So these are just arbitrary values. It is not always possible to use these values for all situations. Okay, so this is the importance of understanding model convergence. So how best is your Kalman filter or any filter matching the realistic values? Okay, and that is once again dependent upon how well you consider the values of Q and R. Okay, so that is what's the importance of considering process noise and measurement noise, right? So coming to the last part, this is what we call the further improvements to Kalman filter models. So that is, as we discussed in the very first slide, it is the adaptive Kalman filter and unscented Kalman filter. So these two are like much more improved variations of linear Kalman filters and extended Kalman filters, where higher order fidelity and higher degree of nonlinearity can be considered here, especially in unscented Kalman filters. So like here the thing is, in adaptive extended Kalman filter, which is given as AEKF, here apart from the regular model, so this is your regular Kalman filter. Okay, so apart from this, we also have an addition to this particular algorithm, and that is called as updating the process noise. So basically, Q was considered static in the previous condition. Here, Q will be updated. So there is a separate set of algorithm for updating Q, which will once again depend upon what is called a signal attenuation factor. So even once again, they're like more study towards signal electronics and signal analysis, things like that. Okay, so there like one of the advanced versions of Kalman filter is this part, where the model actually begins to adapt to the changing values of Q. So it is not realistic that Q is static always. There will be like few changes in Q, and the model actually adapts to this, okay, by using an extra set of algorithms. Then there is unscented Kalman filter. So unscented Kalman filter is like one of the highest fidelity nonlinear filters that you can find in today's filter based methods. Okay, so where basically there is something called a sigma point. Okay, so sigma point is just a statistical representation of the states, where like mean and covariance, variance, covariance, all these values are repeatedly calculated, and they are once again used as a update. Okay, so they're used in the update factor, so the state update. So these parameters once again stay the same, except that here the addition is with respect to sigma points, which is nothing but the statistical properties for the states, the mean and the covariance, right? So these are like some of the advanced Kalman filters which can be used, which is like an improvement over the earlier Kalman filters which was discussed, right? So here we come to the end of the session. So once again, to iterate, we've seen the Kalman filter from start to finish, what the process involves. We have started with initialization. Then we have understood what is a system variable. Then we have gone to predict these system variables called as system state predict. Then from predict, we have gone to see like how the observation matrix will be utilized. Then we have estimated the error. Then from error, we estimate the Kalman gain. From the Kalman gain, we estimate the state update, or you can say the final state. Okay, so this is the complete process, and the whole set of process runs in the loop till such time the final desired state is achieved, or till such time you can say model convergence is achieved. Okay, so with that, we will we have come to the conclusion, or we come to the end of this session.